Hi, everybody. So first off, format-wise, given kind of how this room is laid out and whatnot, just feel free to raise your hand if you have any questions at any point around this. I'm going to be talking about a bunch of different stuff. And today we're going to cover primarily a set of use cases around something that isn't core to this conference from a practical standpoint. So we're not going to be talking about web application delivery or software build and test infrastructure. This is going to be about high-performance computing infrastructure. So today, hopefully, you're going to learn a couple of things. You're going to learn something about continuous and instant delivery and how that helps various aspects of science and engineering be able to do invention and discovery. You'll also learn a lot about some various topics like climate and organic semiconductors and lean manufacturing and technical computing in general. And then I'm going to start off, though, by hopefully helping you learn a little bit about Cycle. So Cycle, we believe that fundamentally getting utility access to technical computing resources is going to be the single largest accelerator of invention over the next couple of decades. And our mission is essentially to help make it so that there's easy HPC for anyone on any resources, whether internal or external, at any scale. And today we're going to learn about a few real use cases. So we have in the past, and not necessarily at this conference, but last year I talked about a fairly large drug discovery use case. I actually have an update to that talk from the keynote last year. We also have a number of new use cases, whether it's rocket design with the Aerospace Corporation or insurance risk management for retirement funds for Pacific Life, or medical device design from Johnson & Johnson. We'll kind of cover a few of these today, just so you have an idea of how we deal with scale and how we deal with continuous delivery in the context of technical computing. So a little about me, I'm a geek from the 90s. So what that means is, essentially whilst I like Hacker News and Reddit, Slashdot is my homepage. So if you've been looking at Slashdot over the last few weeks, there have been a number of interesting stories about the climate. So I'm going to just walk through my experience over the last 4 weeks of looking at Slashdot. So the first one that came up was at the end of March. We had essentially a story about how a UN report had come out talking about the climate changes basically being overwhelming and that they're severe and irreversible of sorts. We also had a study that ruled out whether this was possibly a natural fluctuation. When you have things like a polar vortex happening, a lot of people think that that means there's no global warming. So there was essentially a number of studies done that illustrated very clearly, and this was in early April, that there were no, if you actually control for various factors, this is not a local variation. This is actually the result of the carbon footprint that we're putting down. And if you read some of the news environments about this, the UN report is actually really scary. So it's scary in a subtle way because as an engineer, you think about cause and effect. And essentially what they're saying is that the carbon footprint we have today already will affect everyone. And more specifically, it's going to affect everything from species in various parts of the globe to wildfires, to mudslides, to ice storms, et cetera, et cetera, et cetera. All of the climate variations that we've seen over the last few years where there's been a lot of extreme weather, especially as compared when I was a kid, is not actually just a random occurrence. It's actually driven by the carbon footprint putting down. They've also done a lot of simulations showing that, as opposed to today, a lot of the places in the middle of the globe where we get a majority of our ocean life and a majority of our seafood, we're actually not going to be able to get them. So the red basically marks a 50% reduction in the amount of fish that are available just naturally. So this has nothing to do with overfishing. This is just they won't be able to survive because the ocean water is warmer. There's another simulation that was done that showed the percent increase or decrease. Green is an increase, red is a decrease in the ability to produce food. So most of the breadbasket of the US, for example, in the Midwest, is going to be able to produce far less food decades out than it does today. Places like Canada, however, are going to do quite well. So from hopefully you're getting the picture that this is actually kind of a bad thing, and this is something that actually needs to be solved, not just worked around. You may also be thinking that it's a good time to buy land in Canada. That actually is probably true. But hopefully you're also getting the this is a big deal factor. And just to put a few other proof points on this, the guy that ran the panel that did the study for the UN, the Intergovernmental Panel on Climate Change, basically had this quote that nobody on this planet is going to be untouched by the impacts of climate change, and this was in the context of food delivery. So this isn't anything essentially from a practical standpoint. This is something that we all rely on. This is not just a small change in the weather. There's also a number of US initiatives around climate. It's not just a global issue. So Kerry's quotes basically are a little bit more imperative. The Secretary of State basically says that we cannot deny that this kind of activity is happening, and it's imperative to actually do something about it. So I'm reading all of these, and then the next couple of days after this, so on a day or two later, there's 10 articles about climate engineering and essentially the use of renewables as a potential solution to this. And this is a lot of the reaction that comes back from a lot of the reports that came out at the end of March. And so you start thinking about, okay, well, what is climate engineering? And as it turns out, there's actually a lot of potential solutions to this climate problem. So there's wind power, there's geothermal, there's being able to do nuclear fission, nuclear fusion, there's biofuels, et cetera. There's a number of different ways. Solar, and in particular, is a fairly effective renewal energy that we can take advantage of. So how do we actually simulate and engineer a solution around this? How is it that we would, on a global scale, be able to predict, A, what the changes are, and B, how we can actually impact them? Well, a lot of the studies that were actually done are using a fairly large amount of simulation and compute power. They actually use systems like this. This is a supercomputer based out of NASA. It's called the Pleiades. It's on the top 500. It's actually in the top 10 of the top 500 most powerful computers on the planet. And these supercomputers are great. They're like sports cars. So essentially, they have a really fast engine, but they also have what you call a great interconnect. So all of the nodes can talk to each other exceptionally quickly, which allows you to distribute a very large memory problem like representing the entire global climate across the nodes and have them work effectively together, because it's a tightly coupled problem. It's a problem where the weather in one part of the globe affects everything right next to it, and vice versa all the way around the planet. So that kind of tightly coupled workload generally tends to work only very well in supercomputers. Now the problem with this is that limited infrastructure, when you have a fixed amount of infrastructure, there's always peak versus median utilization problems. And this is implicit in why cloud was so exciting, and why, whether it's internal or external, being able to dynamically provision clusters is actually incredibly useful. In HPC, it's the exact same problem. So the cluster is too large most of the time and too small when you need it most. And essentially, you want to be able to give users a capacity that matches exactly what they need from an infrastructure perspective. So let me switch gears just a little bit now and talk about material science. And specifically, I want to talk about organic semiconductors. So in this space, you have classes of compounds that are not based on silicon. They're not a traditional semiconductor. They're generally based on carbon. They also tend to be layered materials. So specifically in the context of solar, when you're designing a solar material, you have an infinite number, well, actually not infinite, but a countable but very large number of materials that can be in an individual layer. And then you may have 6 or 10 or 12 layers deep in order to build, for example, a solar panel that will turn light efficiently into electricity. So the problem is that organic semiconductors have a lot of very favorable properties, but there are so many of them that it's very difficult to find them. So one of the primary researchers in this area is a guy named Mark Thompson. And if the 20th century was the century of silicon, his quote is essentially the 21st will be around organic, but how do you not spend that entire century finding the proper material? So in his case, we had a needle in a haystack challenge. So what he was looking to do was look across 205,000 different families of materials, which totaled about 264 years of computing. This is essentially a quarter of a compute millennium to do a quantum simulation of photons coming in and electricity coming out. Does this actually generate electricity effectively or efficiently? And you could run this on a supercomputer, and the problem is that most people don't have access to these. These are very, the NASA machine, for example, there's a committee that defines who can run on it and what allotment they get. A lot of times getting access to this kind of machine is very difficult. Thankfully, there's another option. So rather than in the case of this workload, rather than a supercomputer, we can actually use a school bus to take a load of materials across the line rather than an individual sports car. So each job will run slower, but we can do far more of them at once. So this works very well for peak loads where you have like a needle in a haystack problem or a Monte Carlo problem, a big data problem. A lot of these kinds of workloads, a lot of the modern computational sciences fit very well into this framework. So what you really want to do is take all of the interconnect sensitive jobs, put them on the bare metal, the thing that has InfiniBand and runs exceptionally well, and you want to take all of the non-interconnect sensitive jobs and put them, when necessary, on external environments. And in this case, most of the users we have use 40 to 4,000 cores, but this was not his problem. His problem was much larger than that. As we talked about, it's essentially a very 2.3 million hour problem. It was 205,000 way parallel, so we could have done all the materials independently of each other, and they would have worked just fine. So in this case in particular, we spun up approximately 16,788 spot instances on AWS, totaling about 156,000 cores. This was done in a global deployment, so we used all 8 public regions of Amazon to run this workload. What our software does in this context is we use Chef to do continuous delivery of the software and checking of the infrastructure, but we have tool chains around partitioning data sets and moving workloads into the right place at the right time so that you can run a single job from the user's perspective across 8 regions, basically 12 data centers, and that much horsepower from a core count perspective. This actually, when we benched it, as we brought up the nodes early on in our Chef cookbooks, we had one that used the Intel LinPack benchmark, which is kind of the standard benchmark for supercomputers to basically benchmark each individual machine. And we got a 1.21 petaflop. Essentially, this is a half cousin between our peak and our max. It's not a theoretical peak. It's an actual benchmark, but we're not taking into account the interconnect. So we're doing it only at one machine at a time, not many machines together, to basically get a very large environment up. Now, one of the things you'll notice about this that's actually really cool is that in this case, we had, and this laser isn't necessarily showing up on the television set, but it's about 2 hours to get to the 150,000 core mark. So in order to do this work, our engineers actually started working on the problem about 3.5 to 4 weeks beforehand, which is a surprisingly short period of time to set up a cluster run of this scale. In bare metal land, that would have been unheard of. In our case, we were able to basically leverage all of the software we had done before in order to create this environment, and we kept doing it at larger and larger scales. So last year when I was here, I talked about a 50,000 core environment. We actually ran tests that as we were running the test, each test at that point in time was the largest HPC environment in the cloud ever as of that test evening. So we did a 60,000 core test, a 90,000 core test. Right before this one, we actually got 125,000 cores in half an hour. Completely stood up, all running, all using the workload at the same time. Now, the night that we ran this, the actual production workload, there was something else going on inside of the infrastructure, so there were other users using capacity, so it took us a bit longer to actually get access to the full 150. But it is possible, and I expect at some point we're going to come back and report a very large environment that you'll get in 20 minutes. It's going to be unheard of in terms of the size. And normally just flipping the power switch to turn up a supercomputer that's powered down is actually in the better part of a day range. So the fact that we can get this and have it fully up and running is actually very impressive. As I mentioned, we benchmarked the individual nodes and got a performance benchmark. But the key thing is that doing this 264 years of computing actually took 18 hours. And instead of a $68 million machine, we spent $33,000 on it.
Spot instances?
Yes. So this was using Spot entirely. And we actually, when we did this, there's a certain aspect of our software that's fairly resilient. And I'll show a diagram of this and answer questions about it in a slide. But we actually shut down a couple of the regions based on potentially causing problems in the region and also not getting the compute per dollar out of the region that we were expecting. So early on, these 2 shutdowns, we actually completely shut those down. The workload that was running there ran elsewhere. without the user having to do anything. And so this is essentially a dual chaos monkey, chimp, and gorilla proof system. You could turn off an AZ, an individual server, or a region. You could actually do two of them, and we would still execute the entire workload, even if it happened concurrently. So the architecture for this, we have essentially three pieces of software that we write. We use Chef to deploy and execute various administrative functions on all of the boxes as they come up and on a continuous basis thereafter. Cycle Server is essentially a telemetry engine. It basically gets analytics about everything that's going on from an HPC perspective across all of the infrastructure. It's more of a job level and a scheduling layer. Data Manager basically moves data and it knows a bit about workloads and how to partition data sets and move them and transfer them and keep audit trail on them, very similar to how Chef has a traceability component to it. And CycleCloud basically does cluster orchestration at massive scale. So it's very good at, we have essentially a container methodology, much like Docker inside an OS. This contains multi-server clusters and allows them to be spun up at very large scale. So we ran essentially a distributed queue that we wrote called Jupyter, which is allows large clouds to work together. Essentially, it ran in each region as a head node. There were 8 of those regions in play, 14 nodes managing the 16,788. We think the engineers basically that worked on this thought that we could have gone as low as potentially 10 nodes controlling that many, but for resiliency purposes, we didn't want to have a production workload like that, just hitting what it could potentially use. So we actually had a little bit of extra management nodes in there for resiliency purposes. And then, basically this one could have survived 2 failures without issue. And in fact did as we shut down 2 regions. Not only that, we used Chef, obviously, to do the deployment and configuration, and then continuous, we basically have code bases around error handling and other things that we use Chef to implement as this is going on. And now Dr. Mark Thompson's actually analyzing all of the simulations that came out of that and looking at the most valuable families of compounds in there. I'm actually hoping that in the next 3 to 6 months I'll have an update where I can say he found one that was this % more efficient than the prior known one is, but hopefully this is something that will lead to a far more efficient way of doing solar power. So with that in mind, basically, how else is this important? Where is this important? And it turns out that solving this problem is actually a critical problem across a lot of different industries and has happened before. So if you look at manufacturing capacity, for example, so history repeating itself, lean manufacturing, the notion that came out of essentially Japan in the mid-20th century was an attempt to deal with multi-stage processes that have different forms of waste and be able to reduce waste in a way that makes it very continuous to get raw materials turned into final inventory. This process is almost exactly what everybody's been talking about at this conference from a continuous delivery perspective, where we have a modern software process to continuously turn builds into production applications. It's exactly the same thing, just different terminology, different industry. And this is happening across lots of different industries. So I'm going to try and give you a little description of why this is happening. And we work with a number of different verticals, everything from insurance risk management through defense. Essentially, users want to decrease what is called in lean manufacturing cycle time. And we didn't name it cycle computing 9 years ago because of this. We just found out about this last year. But in the meantime, the cycle time is essentially the prep time plus the queue time plus the run time. So this is your human effort, your queue wait time, and your run time. That's the amount of time it takes you to get a result when you're running an analysis. Now, if you'll all recall from high school, there were a set of steps in the scientific method where you might ask a question once, hypothesize, predict 2, maybe 3 times, and then be able to deal with experimental test and analyze many times. So in Monte Carlo simulations, you're potentially doing this millions. In this case, we're doing 205,000 individual little experiments about each material. And then you get your final results and you do your analysis on it. So any incremental change that we can make to that inner loop to make that more efficient essentially yields multiplicative benefits. So if we make it far faster to get one of those back, or more particularly 205,000 of them at a time back, we make the entire process that much shorter. So what's holding this process back in different industries that we deal with? It's almost always the utility access problem. So, essentially what we try to do is use Chef and our software to continuously deliver HPC capacity to the human brain of the person using it, so that you can solve what has become a pretty pervasive bottleneck. So in most of the customers that we deal with, and this doesn't matter whether it's Johnson & Johnson or Pacific Life or AIG, all of them are essentially running into the problem where scientists generally have to size the questions, the expectations of what they're going to do to the infrastructure that they have access to. And that's not really what we want. We want them asking the right question, the big one if it matters, in order to be able to do the proper analysis. So essentially how cloud helps with this is it allows us to put, as I mentioned before, the important fast interconnect jobs on the fast interconnect machines, and then take all of the other job workloads that generally also happen on these environments and put them on cloud when needed. And the workloads are actually helping us with this. So it used to be that these tightly coupled MPI jobs, they would essentially only be run once. So you'd run a simulation of a potential CAD design once, and then you'd be done. Now people are doing Monte Carlo, so they're essentially running the same simulation but with different conditions, or a parameter sweep with different conditions. And that creates a large number of jobs that need to be executed. So rather than waiting for all three of them to finish, in this case, one right after another, we can actually run them concurrently. And in this case, the dollars per science and the throughput is actually just as important as individual performance. Because if we can get all three of them done far faster, even though those three may take slightly longer, the overall job runs incredibly quicker compared to a traditional model. So this is something that we've seen pretty universally across different industries, and I'm going to go and talk to you about three of them in particular in the context of a deployment, and this is generally what a deployment looks like for us. So we would have essentially jobs and data coming in, we'd have an internal HPC environment that would be running a majority of the workload, we'd be moving data where necessary externally, and running a up to massive cluster, but generally it's 40 to 4,000 cores externally, and we're using Chef to essentially make sure that all of our configuration and error handling and other pieces are the same across all of the environments that we're using to run the workloads. And this is basically something we've been doing for 9 years now, and have a tremendous amount of experience in it. This is kind of the area that we're the gorilla in. So the three use cases I'll talk to you about are drug design, so I have a follow-up to last year's talk. I also have another one around engineering, specifically rocket design and hard disk design. And then I have another around essentially RNA analysis and genomic analysis online. So talking about drug design, I've used this slide before at ChefConf last year, but there's a very large number of diseases where the number of people getting them is radically increasing, and in this context, every day is very important. Anytime you can shave a week or two off of a drug design process is a good thing. So in this case, we had Novartis, who had 341,000 hours of computing that they wanted to be able to run against a cancer target. So this is a lock and key problem. You have a protein, you have a set of compounds that may be fits, and you, again, needle in a haystack side, want to find out which of the 341,000 hours that you're simulating these compounds, which of them are the most valuable and have the best fit. So Novartis, in this case, did a bunch of instance benchmarking, and this is something that we've used Chef to automate from a practical standpoint, as well as our own software. So that table, this is a slide that Novartis used at a talk at reInvent in AWS last year. But essentially, we take automatically the workload that they want to run, a represented sample of it, and we run it in an automated way across all different infrastructure types in appropriate quantities so that we can give you dollars. These two columns on the right-hand side essentially are dollars per 1,000 jobs run. So you have a very clear idea of what instance types are most beneficial to the workload that you're running. And then in this case, we actually spun up 10,600 instances to run the 340,000 hours of computing. The AWS console, this is the only part of the AWS console that rendered. We didn't get the AWS logo. We didn't get the table. We didn't get the server listing. We just got this. But you can see here that there was, at the time we snapshotted it, 10,598 instances that it was tracking. And then this was our view of that same cluster. So we essentially got retina displays for everybody after this. But we had approximately 100 by 100 grid of 10,000 servers. And the ones that are marked in green, everything is fully functional. The ones that are marked in red, either a combination of our software or the Chef converges that we have running every few minutes on the infrastructure, was identifying some form of problem that needed to be addressed. And in this case, the 341,000 hours ran approximately, I believe it was in 11 hours. So we didn't use $44 million in servers, which is what that server count normally would cost. We did it in about 11 hours, and it cost $4,372 in infrastructure. And in this case, it did actually lead to 3 new compounds going into the wet lab, which is amazing. You normally don't get that kind of result. It's because they were able to ask the right question and not the one that just happened to fit on the couple of thousand cores they had locally. Engineering, same thing. Any questions about that use case? I might as well. Awesome. All right, so I'm going to just run through very, very quickly similar use cases, but slightly different in each one. Aerospace Corporation. They do the rocket design for the Apollo missions and putting Curiosity on Mars and what have you. It's actually a really cool set of simulations that they're doing. Essentially, at that organization, they want to allow engineers to focus on the science and the engineering aspect of what they're doing. They do a lot of Monte Carlo CFD simulation and other things. And we basically want to reduce or eliminate Q8 time for them. We want to make it so that users submit something, it starts running immediately. As soon as it's done, they get a result back. So we started working with them the summer of last year, so after ChefConf being the point. And essentially at reInvent in November, we had them fully up and running on a GovCloud implementation. So this was a very interesting one for us because there was a lot of automation that we used Chef for around various aspects or peculiarities of GovCloud. And then we ran basically a set of nodes up to, I think, about 3,000 cores on VPC in order to run the burst off of their internal cluster. And again, it was primarily for Monte Carlo sets of simulation jobs that they were running. I believe the implementation looks like this. So essentially, they have a file system internally that's some number of terabytes. Externally, it's tens of terabytes and basically an auto-scaling cluster. And again, the idea was to remove the caps on scale, but also get rid of Q8 time. That was the really important part for that one. HGST, they make hard drives. They made the 1-inch hard drives that were in the original iPods. If you remember back like 10 years ago when we actually had hard drives in iPods. They had the 1-inch drives that had 30 gigs of capacity, et cetera. They're now a Western Digital company. And so they talked at reInvent as well about essentially their HPC stack. I'm going to summarize what he said, but it's actually really cool, the science they were doing. So when they simulate a hard drive, they are not only simulating the spinning disk and the airflow around it, and that's why you have these drives that now have various inert gases like helium pumped into them. In order to have basically a dense gas or a gas with a proper airflow so that the disk can spin as fast as possible. But they also simulate the molecular dynamics of the grease that they put on the spindles. They simulate every aspect of that mechanical device in detail. When it's an SSD, same difference, but it's now all the circuit boards and all of the signals for essentially reducing heat and making it so that the SSDs will function really well. So they have a very interesting set of technologies that they use, everything from the molecular dynamics to computational fluid dynamics of the spinning disk drives. And the CIO got up and talked at reInvent essentially about, again, a burst use case. But the really important thing for them was they had a Hitachi supercomputer that they described that they were using that was older. It was probably 3 to 4 years old, but it was a 512 core custom machine. And instead, we were able to get comparable performance, but you could spin these up in 10 minutes and then turn them off when you were done. And not only that, you just didn't have one of them, you could have 10 of them running concurrently. So it totally changed the way the researcher interacted with the environment, because now, thanks to this kind of reproducible, traceable, easy to deploy, basically continuously delivered compute capacity, the workflow for them changed radically. They weren't waiting one right after another for simulations to finish. They could now do things concurrently and be more efficient. So this was a huge deal for them as well. Lastly, I'll cover ion torrent because this is a slightly different use case. So these are analysis as a service. So this is actually a really interesting one. The ion torrent machine is essentially built by Thermo Fisher now. It used to be Life Technologies. They got bought. It's a little desktop device that creates essentially full genomes out of samples. So you give it tissue samples, and it'll create a set of reads that then have to be aligned against a reference, and you have your genome in its entirety, GATC essentially, all of them, all 3 billion of them. And that process and doing some of the analysis on that is something that is sometimes too compute intensive for the owner of the desktop machine to be able to use, specifically like a doctor's office. So some of that gets done online via an upload and an analysis and what have you. All of that is essentially being done in a central place. So rather than having one user that's asking one big question, there's essentially a population of users that are all concurrently asking questions. This is a very large multi-user environment. And so in this context, we use Chef essentially to deploy a fairly complicated cluster that has application servers. It's got NoSQL databases. It's got a large parallel file system, and up to about 8,000 cores of analysis infrastructure, HPC infrastructure alongside it, all of it managed by a combination of CycleCloud and Chef in order to provide basically continuous delivery of compute power to that population of users. So it's essentially a multi-tenant system. One of the things we found Chef was really good at in that context was actually providing some of the wipe up and cleanup and checking around the sandboxing side. So when you're running a job and you want to sandbox one user's data from another data, you have to do special wrappers, obviously, around the workload, but it's always good to have a mechanism for determining that that's actually being successful and constantly checking it on a continuous basis, and we do use Chef for doing that. It also is a very complicated environment, not just an HPC cluster. This actually had many roles in this one system, and Chef scaled terrifically in basically doing this. So now hopefully you believe that you can use utility access to this to accelerate invention, that supercomputers are great, but we can also get a lot of benefit out of pleasantly parallel workloads on cloud. Also that we can potentially revolutionize material science. There's a lot of sexiness around genomics nowadays, but I actually think material science is going to have a very large amount of impact over the next few decades, and a lot of what's going on in computing right now and automation to deliver that to a researcher is actually going to have a big impact there. Hopefully you also got that we need to engineer solutions for climate and actually start looking at that as an engineering problem, not as a freight train that we're going to sit by and watch it kind of happen. You may have gotten that you need to buy land in Canada, and that we can essentially solve this problem. We can do it across a number of different fields that are all vastly unrelated, and use essentially Chef and in our case our software, but to continuously deliver HPC to accelerate the human mind. And that's basically what we do. If any of this resonates with you, if you like this area at all, we are hiring a lot right now. So please feel free to come up to me or just send your email here. And in the meantime, I'd be happy to take any questions that you may have. Any?
So with that kind of skill, how many failures do you?
Depends on the error type. So there's probably, one of the things that we have is a taxonomy of different errors that occur. And if something happens at, a half a percent error rate, right? Like your ephemeral drive is not mountable by the native OS, then we'll see it, 0.5% of 17,000, we're going to see 85 of those, right? So generally what happens in our software, and we have a large built-up capacity of different kind of immune system responses, essentially, where over the years we've done, in 2010, we did a 10,000 core cluster with Genentech that we published. We've publicly done a 30,000 core cluster, a 50,000, a 10,000 server, a 17,000 server, 150,000. And then we have our customer users that don't want to talk about what they're doing and all of that usage. So as part of that, essentially, we have a fairly intricate map of the different error rates that would happen. There's probably between 10 and 20 different error types that all have about that low frequency on AWS infrastructure. Other infrastructure like your internal systems or other providers even have essentially their own fingerprints around the kinds of issues that they have. And there's different ways of solving each problem. And there's also different ways of reacting to it. This is where we have a lot of IP. So we've been doing this, we've been doing Cloud HPC since 2007. So we basically have a lot of software and IP around these immune responses. And okay, well, actually in this case, we want to hold and then acquire a new resource and then release so that we don't get this one back, et cetera. All of those kinds of things we had to do 7 years ago before Chef was around, so we were doing it in an awkward way. And then in 2009 and 10, we actually started using Chef pretty heavily to automate various aspects of that. And so now Chef essentially serves as an execution engine for a lot of the code that we have to create production environments at scale.
So you were the guys, like when AWS was going down, probably because you were setting up.
We have caused problems, but we have not taken anything down. We have stuff that detects when we're getting failures and backs off appropriately. We try to be, yeah, I mean, we're trying to benefit humanity, right? Okay? So if we go and stomp all over everybody else's usage, it's not really useful to anybody, right? So we do have back off stuff. We do have like, okay, we're getting throttled clearly here. APIs may be consistent. Backwards compatibility is definitely there on most of the APIs that are publicly published, but the behavior of them is different. So how does it behave when I actually make the call to get the instances? Sure, the over-the-wire protocol is exactly the same, but my response back and the timing and the way that happens is different over time. And you can tell if you pay attention to these things, you can tell when there are major software releases that your cloud provider's done, et cetera. So those are the kinds of things that we've basically built code to deal with over time. And we have to because of the scale. And what that does, and it's interesting too, because I think a lot of people, for us, it's always a challenge. So I'm a bootstrap startup. I have no investors. I've got a majority of the big 8 pharma, 3 of the 5 largest insurance life annuities like AIG, Hartford Insurance Group, et cetera. A large number of manufacturing, life sciences customers that are not big, but are in kind of mid and small tier. But people think of us primarily because of the large runs. But what that really actually benefits, and kind of what your question gets to, is the small runs run that much more reliably because we've seen all of the error conditions that essentially happen. So now you don't have to worry that when you spin up this 10-node cluster that's running a build environment or running an automated test, that one node is just going to randomly be weird, and you're not going to, you're going to have to, oh, well, crap. Like that doesn't happen as much anymore for us, which has been a really helpful thing. But getting back to make sure I concretely answer, I'd say there's probably 10 to 20 big ones that tend to happen. But the list, it changes over time, and essentially, there are sometimes it's recoverable, sometimes they're not. It really depends on the detail. And unfortunately, I don't get to do the fun stuff anymore. I was coding up until about 4 or 5 years ago, and now I don't get to. So I'm sorry I didn't give you a detailed, juicy, technical, here are the APIs we use talk. I would love to have been able to do that, but they asked me to do this talk about a week and a half ago, and I said, sure, I'll come out and do it. So in the meantime, I'm sorry about that. But any other questions? That was a great question. Please.
When you walk up to a company, do you deploy their code, or do they interface with your structure?
So we have two general scenarios. So the question was, when we work with an organization, do we use their code, or how does that work? What's the handshake there in terms of deployment and Chef and what have you? So we use Chef to implement essentially a template that is pretty easy for non-DevOps people to just get us the applications that we can deploy. We also have a lot of users that use Chef and have talked at this conference or others about their use of Chef. So we do have that. I think J&J is one of them that's publicly said they're using the open source version internally. So that template supports using your native Chef recipes and roles and what have you within it. And there's also the second use case of we have a cookie cutter application. So for example, if you're running computational fluid dynamics. Most of the applications that do that, we have something where you push a button and there's a cluster, and it's got options around a parallel file system or just an NFS mount, depending on your performance needs and versus cost trade-offs. On the infrastructure stuff, like all of that is already entirely mapped, and it's very well tested, and it's been used a million times, et cetera. So we have those kinds of things as well, where there's not necessarily a proprietary application that I've written that's running, you know, a retirement fund risk analysis model, which is custom to me, but it's an open. I want to run weather simulation, which is WRF, the weather research and forecasting model, WRF. So we can spin up a WRF cluster now very easily. You know, that kind of stuff is really straightforward. So those are the two usage patterns really when we deal with a customer. It used to be in 2007, it probably took us a couple of months to get a cluster fully vetted and productionalized with the user's application, or maybe a month. Nowadays, it's like an hour or a day. And then a lot of that's thanks to the automation that we're able to do with Chef. We can make it very easy to just have this stuff be a push button item or run this command line and you've got the cluster type you're looking for or whatever. Yeah, that's a great question. Any others? All right, yeah, I think we're done. We're wrapped. If you have anything else for me or you're interested in the job, let me know. And thanks again.